Hello. How do we model single degree of freedom undamped systems when they are not subjected to any force or under any loading, but they are just under free vibration? So what is really free vibration? How a system oscillates or creates some motion if they are not forced? So here there are some videos of our equipment, 3D printed laboratory equipment for vibrations and control laboratories. I have a compliant parallel arm mechanism consisted of a mass, a sliding mass with 1, 2, 3, 4 springs and 2 springs on both sides. So free vibration means, yes, we are not going to apply any force or torque on a system, but instead we will provide an initial displacement while reading data from the system. So this is a translational system. In the second example here, we have a cantilever beam. Cantilever beam itself is just a flexible beam, and it once you push at the tip and release it, it will start vibrating. But you can also attach more springs to change this overall stiffness of the system. So what we are doing, we're attaching an accelerometer at the tips to do system characterization, such as finding the Young's modulus of this 3D printed flexible beam. Yes, this is free vibration because we displaced, and after we released the cantilever beam, we were not applying any force. That simply means free vibration. Again, free vibration means from the moment that you started the motion by displacing, simply by even applying a force at the tip for a cantilever beam, for a slider, displace it to the right or to the left, and then release. For a rotational disc here, what you can do is you will just rotate the disc because this is also a single degree of freedom, and once you release, you're not applying a force anymore to the system. Here there is another one. We have a pendulum. This is also an example to a 1 degree of freedom system. The pendulum, you can just rotate to an angle and release from that position, and while you can collect data from the encoder. The next example is not a single degree of freedom system, but this is a 2 degree of freedom system because we have two masses and they are only allowed to move along the x-axis. And this example is also a 2 degree of freedom because we have two cars attached to several springs and they are only allowed to move along this rail. So seeing some examples, let's now continue with the free vibration of single degree of freedom systems theory. Yes, starting with this simple mass spring system, which is attached to a card, because we started with the first title as undamped, and it means, yes, not practical, but assuming that the system has no friction associated with it. To be able to draw, because it's a single degree of freedom system, you can either apply Newton's laws of motion or you can use the energy methods. Because there is no friction, energy will be conserved as the card moves from one point to another. So here, assume that the card is moved to the right. Once you move the card to the right and looking at that, the spring is a fixed free spring, meaning that one side is fixed or grounded while the other end is attached to the slider. So if you displace the slider to the right by x, then it means you're stretching the spring to the right by x. Then the spring force acting on the slider should be to the left, because spring forces are opposing forces, by k times x of t. And I can actually say that this x is a displacement which is a function of time. Now let's apply Newton's laws of motion. Total force is equal to mass times acceleration. To the right on the sketch is assumed to be positive, so the spring force should be negative, equal to the inertia term, mass times acceleration. So when you write the differential equation, in the general form, you just put the inputs to the right. The system has no applied force, and it means the right side will be equal to 0. And writing the differential equation starting with the highest derivative term in a descending order, you should get to the mass times acceleration plus k times x, which is equal to 0. This is a linear equation, second order linear, and a homogeneous differential equation. We can get to the same equation applying the energy equations, energy conservation. The total kinetic energy plus the total potential should be constant during the motion. The kinetic energy will be due to the mass, which is 1/2 m times x dot. Here x dot is the speed of the card squared, and the potential is due to the springs. So it should be 1/2 times k times x squared. The sum should be constant. So once you add these two energy terms together, knowing that the right side is equal to a constant. Once you take the derivative with respect to time, the right side, because the derivative constant is 0, so the right side should be equal to 0. We can actually factor out this equation by x dot. X dot is the velocity, and you get to mx double dot plus k times x multiplied by x dot, which is equal to 0. I always give this example in my classes. You have two products, a times b is equal to 0. To be able to accomplish this, either a should be 0 or b should be equal to 0. Or in the most generous case, both terms can be equal to 0. Because the velocity is not expected to be 0, we assume that mass times acceleration plus k times x should be equal to 0 from this equation. As you see that we derive to the same equations. So, okay, we get to the equation of motion. What is next? How we are going to solve this problem? Probably we are trying to find the position of the card at any time. So where is the what is the card's displacement when t is equal to 3 seconds is what we are trying to solve. So this equation, in its most general case, assuming the highest derivative is equal to 1, so we divided both sides of the equation by m, getting to this form, x double dot plus k over m times x is equal to 0. But here, to be able to solve this problem, you should know the stiffness and you should know the mass. There's another way of representing the same equation using not the system parameters such as mass and stiffness, but its natural frequency. Because if you know the natural frequency of the system, then you will have a better sense of how many times a system oscillates. So I have x double dot plus omega n squared times x is equal to 0. Since these two are the same equations, then you can make an analogy so that the omega n squared, which is the coefficient of x, should be equal to k over m. So the natural frequency in radian per second is equal to square root of k over m. If you know natural frequency in radian per second is also equal to 2 pi fn, so here fn, which is the natural frequency in hertz, will be also equal to omega n over 2 pi. And we also know that if you know fn, you can find the natural period of the system, which is the reciprocal of the same number. Next, yes, let's just get into details about this omega and fn and tn. Assume that you have a mass spring system. As I showed in the videos, you can attach an accelerometer from a free vibration single degree of freedom system because there is no energy loss, there is no friction in the system. You expect that initially if you displace the card to a point, once after you release, the card is expected to oscillate back and forth around its initial position 0. So from this experiment, if you collect the data from an accelerometer or for a pendulum example from an encoder or for a rotational disk from a potentiometer, and you can actually, if you plot the displacement versus time graphs, the distance, the elapsed time between the two peaks gives you the natural period. If you know natural period, then you can calculate natural frequency in hertz, and knowing the natural frequency in hertz, you can actually calculate the rotational angular velocity 2 pi fn, which is omega n experimental. Yes, this is the calculation through experimental data. That's why I will call this omega n experimental. Let's say you know the mass, but you don't know the stiffness of the system. Maybe you 3D printed the system. Maybe the geometry is difficult, a little bit complex that you don't know how to apply the equations. So there's an unknown in the system, such as in this one, stiffness is the unknown. So from here, omega n was equal to square root of k over m, which is 2 pi fn. Yes, you already know omega n, and omega n squared is k over m. And if you just start with Fn, you can actually use this equation to calculate the stiffness of the system. The reverse is also correct. If you know the stiffness, you can find the mass of the system as well. Let's go back to the equations and how we actually theoretically find the position of the card at any moment for single degree of freedom undamped systems. So this is the equation written in the general form using omega n. Remember, this equation can also be written as x double dot plus k over m times x, which is equal to 0. A trivial solution, when I was an undergrad student, I never understood what is a trivial solution. So my professor started with saying that, hey, assume that c times e to the rt is a solution to this problem. So I never got that. How do we know c times e to the rt is a solution to the problem? Actually, we really don't know if this is a solution to the problem. What we simply do, a trivial solution means, let's say 1 plus x is equal to 5. Yes, x will be equal to 5 minus 1. But with a trivial solution, you assume that if x is equal to 0, we are trying if x is equal to 0 is a solution to the problem. So what I'm going to do is I'm going to go back to my equation and plug in 0 for x. So 1 plus 0 is not equal to 5. So x equal to 0 is not a solution. Let's try x as 1. So 1 plus 1 is not equal to 5 as well. So this didn't work. And you keep trying different numbers. Let's say you will try next time x is equal to 4. So 1 plus 4 is equal to 5. So this is how I know x is equal to 4 is a solution to my problem. Trivial solution means we will try an equation and then we will go back into the equation and plug that in. And if the right side is equal to the left side, then that solution, that equation is a solution to our problem. If x is equal to c times e to the rt is a solution to the second order differential equation, then let's take its first and its second derivative, plug that into the main equation. Wherever we see x double dot, we plugged in cr squared ert and then omega n squared multiplied by just x of t, which is equal to c times ert, is also equal to 0. If you factor out the equation by c times e to the rt, it gives you r squared plus omega n squared. We already know that there's a product of two equations, which is equal to 0. And because exponential function can never be equal to 0, there is only one way to make this product equal to 0, is r squared plus omega n squared should be equal to 0. So this is actually your characteristic equation or auxiliary equation. In this one, r squared, which are the roots of your equation, should be equal to negative omega n squared. And the square of a number cannot be equal to negative, then it means we don't have a real solution but a complex solution. So what does that really mean? Going back to your differential equations class, when we have a table. If your equations, if the characteristic equation roots are real and distinct, then the solution should be c1 times e to the r1t plus c2 times e to the r2t. And in the second case, if your second order characteristic equation roots are double, then it means they're equal to each other. Let's say r is equal to r and r, or r1 and r1. Then the solution will be c1 times e to the rt plus c2 times t times e to the rt. But if you have complex roots, then the solution should be e to the alpha t. Here alpha is the real component and beta will be the complex part of your roots. When I look at my example here, r was equal to plus or minus omega n times I. Then it means it's not real, it's not double. I have a third case, which are complex roots. So let's see, my equation does not really look like alpha plus or minus beta I. So my equation was simply plus or minus omega n I. But this can also be written as alpha plus minus beta I, then it means the real component is 0 because I have pure imaginary poles. Beta will be equal to omega n. Now I can just go ahead and plug that in. E to the 0 will be 1, so that will disappear from my equation. That gives me only a times cosine omega nt plus b times sine omega nt. You can also go ahead and find, this is the general solution. We don't know the initial displacement. There are no initial values provided to us. So this bubbled equation will be just a free response of single degree of freedom undamped systems in its general case. But then let's say you know some initial conditions. You know that you displayed the car to the right by 3 centimeter, 5 centimeter, 1 meter. And maybe you just provided an initial displacement. Initial displacement is, let's say, 3 meters per second. So how do we find the particular solution to this problem? So x of t was equal to a cosine omega nt plus b times sine omega nt. Assuming that the initial displacement is equal to x sub 0 and the initial velocity is equal to x dot sub 0. So from here, let's go ahead and plug in 0 for time. So x0 is equal to x0, cosine 0 is 1, sine 0 is 0. That term will cancel out. This should only give you the initial displacement as equal to a. So we know A. We know what A is in terms of system. system parameter. So that's equal to the initial displacement. Let's now differentiate your equation. So that will give you negative a omega and sine omega and t plus b omega and cosine omega and t. The initial values means we will just plug in 0 for time. The initial velocity here will be equal to sine 0 is 0. That only again gives you b times omega and times cosine omega and t. But remember here, we already know cosine will be also equal to cosine 0 will be 1. So from here, b should be equal to initial velocity over omega n. Now the particular solution to the problem, knowing the initial displacement and initial velocity, the single degree of freedom undamped system response should be equal to initial position times cosine omega n t plus initial velocity over omega n times sine omega n t. From this equation, you can easily calculate the position of the card when x is equal to time is equal to 10 seconds or even 100 seconds.